my name is Jennifer. In today's lab, I'm going to discuss the motion of a falling object as affected by different forces and modeling the ways which we can predict this motion. Here's a video of my system. A sheet of A4 paper crushed into a ball, falling in a relatively straight path to the ground. We are interested in modeling this motion in order to understand the components of the physics principles which drive this motion. Before discussing numerical observations, we need to get an idea of physics concepts affecting the ball's motion, namely the momentum principle, or Newton's second law, which states that a change in momentum is associated with a net force on an object, giving the equation that the change in momentum over the change in time is equal to the net force. Combining the momentum principle with the equation that momentum equals mass times velocity, we can note that a change in velocity means that there is a net force acting on the object. First, we are going to investigate if there is a net force on the ball. We derived that a change in velocity is associated with a net force, so we can use the tracker software to analyze the ball's position over time. I initialized the coordinate system at a slight angle due to my camera sitting on an angle. I marked the position of the ball during every 0.33 second interval frame for which the ball was in between being released from my hand and hitting the ground for the first time. The distance was initialized by marking my baseboard, which is 10.3 centimeters or 0.103 meters long. Looking at the graph of the y position over time, we can see that the change in position increases per time interval in later frames. Further into the negative, since the y-axis was defined as negative being down. This indicates an increasing velocity, since velocity is equal to position over time. Since there's a change in velocity between each time interval, we can say that there is a net force. Knowing that there is a net force on the object is not quite enough. Another important part of analyzing the net force is understanding the components that are added to yield the net force. For a falling object, there are two main forces we will discuss, the first being the gravitational force, or weight, and the second being drag. The gravitational force is due to interactions between the mass of the ball and the mass of the Earth. Since the ball is relatively close to the Earth, we can approximate Fg as mg, as shown by the derivation here. Drag, or air resistance, is the second force we are keeping in mind. It can be thought of as friction by the air, as the air molecules push around the direction opposite of motion. The equation for drag that we will use is some proportionality constant, b, multiplied by the velocity squared. Now we are ready to incorporate these forces into our computational model of the ball's motion in GlowScript. Some important parts of the code to mention include the initialization of mass, which I approximated as 2.93 grams or 0.00293 kilograms. The initial position is the zero vector, since I defined the initial position in the ball as 0 in tracker. The velocity also begins at 0, since the ball is dropped from rest. First, we are going to look at the motion of the ball with weight as the only force. Later, we will incorporate drag, but for now we can ignore the drag force since it is multiplied by 0. We use the momentum principle and iterate through the position and velocity update formulas with small time intervals to track the ball's position over time. We can see that toward the beginning, the positions that the program calculates are reasonably accurate. However, toward the end of the dataset, the model predicts the ball to have moved more than it actually did. There must be another force in the opposite direction that accounts for this deviation. Therefore, we will incorporate drag into our position calculations. It is given that drag is equal to a proportionality constant b multiplied by the square of the velocity, so we calculate it as so. It is important to note that Python will not allow you to raise a vector to a power, so I redefined the vector and squared the y component of velocity. Squaring all the components threw an error. And since the x and z velocity components are 0 regardless, I just did not square them. I then used the guess and check method to estimate b, with b being that value that ran and matched the final position of the ball in my real-world observation. We can see that the observed position over time matches more closely to the estimation including both drag and gravity. However, there still is a small discrepancy toward the end. One reason this may have occurred is due to my own error. Since the ball was speeding up toward the end of the video, it became blurry and more difficult to identify the center of it in tracker. Additionally, there are certainly more accurate ways to define b and drag overall. However, we are not yet at that level of complexity in our course. The discussion of drag and gravitational force warrants a discussion of terminal velocity, which occurs when the force of drag becomes equal to the gravitational force, and thus the object does not speed up any further. We can see within the time frame of my observation that the ball may have been approaching terminal velocity because the change in the slope between 2 points on the graph began to decrease. However, if I dropped the ball from a greater height, we may have been able to observe the slope become a constant at the end, since there would be more time for the drag force to increase. Another way we could have observed terminal velocity is if I threw the ball downward with a force. Since the drag increases with increased speed, by an exponential factor when the speed is squared, the ball having an initial speed greater than 0 would have resulted in it reaching its terminal velocity more quickly. To test the idea that an initial velocity results in a faster approach to terminal velocity, we can give the glow script model an initial velocity of 0, -1, 0. We can see that even within the same period of time, the slope of the position over time approaches a constant rate of change. For me, the main takeaway of this lab is that we can revise our models to make more realistic simulations of the world around us. Thank you for watching. The link to my code is in the description if you wish to explore further.